which is slightly different from the one I have up here. I said I was going to talk about two aspects of satellite remote sensing. First of all, deformation measurements on a global scale, and then also volcanic degassing. So particularly that's measurements of cloud properties and aerosol. So I'm still going to do that. I'm going to start off talking about satellite deformation measurements and lead into talking about a method for doing signal analysis with very large global data sets. So though it's kind of quite technically applied to INSAR, to interferometric synthetic aperture radar data here, it's broadly applicable to other kind of three-dimensional spatiotemporal data sets, which might be quite useful in other fields. So to give you some context, why are satellite data interesting for volcanology? And I think one of the main reasons is that, particularly this is an example of satellite radar, we've seen an order of magnitude increase in the amount of data that's available over the past few years. So particularly since about 2008, 2009, we've number of satellites with SAR-capable instruments on them has increased by a factor of kind of 5 to 10, depending how you count it. But beyond that, the quality of the data has improved. So we now have data that are freely available from some satellite agencies, unfortunately not all. We have higher spatial and temporal resolution data than before. And importantly, we have background missions which have a commitment to acquiring overactive volcanoes in a systematic way, which means these data are increasingly useful, and they kind of allow new approaches in volcanology to looking at systems globally, comparing different systems, instead of forensically studying one system in detail. And that's useful for looking at some kinds of problems and not others. And I think it's a kind of exciting area of research that you can apply to many different measurement methods. So we've now at a point, we've got about 340 measurements of magmatic and volcanic deformation around the world at 200 odd volcanoes. So for people who aren't familiar with it, the method that I'm going to be talking about is called INSAR. It's a measurement method that allows you to make measurements down to a precision of centimeters to millimeters at the Earth's surface over swaths that range kind of from 10 to 50 kilometers to hundreds of kilometers. The principle behind the method is that we have radar images that have an amplitude and a phase component, and we use the difference between two phase components to map deformation. So if I talk about fringes, that's complete color cycles. Each complete color cycle there represents a finite amount of deformation, and we can use images like this, found from radar phase differences, to map out the deformation of the ground surface. So this is a little bit of motivation is why I think it's important to try and look at satellite measurements on a global scale. So this comes from my PhD research. So my task for my PhD was to look at 3 years of radar data from this Japanese instrument from JAXA over the Central American volcanic arc. And there's a lot of really active volcanoes in Central America. Over the time that I was observing, there were several new lava flows, there were explosive eruptions, there was a lot of activity. And I did find a couple of interesting signals associated with structural deformation. So new lava flows being emplaced at San Chiguito in Guatemala, lava domes being built up, interesting kind of slow collapse features of the post-1968 lava flows at Arenal. But probably the most notable thing from looking at this data set was that actually there wasn't any deformation that we could really pin down to being associated to magmatic intrusions in Central America. And that's a surprise given how active that arc is. So one of the first things I tried to do at that point was to say, okay, is this actually surprising? So this chart here shows the top bar there in grey shows the number of historically active volcanoes at each arc around the world, and then in orange and in yellow, the number of INSAR observations of deformation. So the ones you want to look at are really the orange ones, which show you magmatic deformation. And I thought, well, how do I work out if this is actually significant or not? So the very basic way that I tried to do that was using a Fisher's exact test of independence with a null hypothesis that all historically active volcanoes are equally likely to produce deformation in a way that's measurable with INSAR. So that's the thing to try and disprove. And if you apply this sort of analysis to the global data set, you end up with something like this. So focusing on the bottom line there, a p-value that's significant is below 0.05, and there are 3 volcanic arcs where you have either more or less deformation than you'd expect from looking at the global data set as a whole. And those places are in the Central Andes, where you have way more than expected, in Alaska and the Aleutians, also way more than expected, and Central America, where you have much, much less given the number of active volcanoes. So there's a few ways that you can try and explain this, and that's really where the rest of this talk is kind of get at. The first is that it could be just something associated with our measurement method. So the less interesting possibility is the reason we have lots of measurements in the Central Andes is that it's very dry, it's relatively high, it's a good place for making satellite radar measurements. But that doesn't really apply to the Aleutians, which is quite a difficult place to make measurements because of the intermittent snow cover. And we also see a high number of deformation measurements there. The more interesting possibility is that it tells us something about the kind of average magma storage conditions at the different arcs. So for example, you could plausibly say that in Central America we have less magmatic deformation because magma rises from greater depths immediately before eruptions. The ascent of magma might be faster. Where you do have shallow storage, you might expect there to be greater volatile concentrations. This is kind of a hard thing to demonstrate. And if you compare the INSAR estimated depths for magma reservoirs in different parts of the world to the depths that we estimate from petrology, we have quite an interesting mismatch between those. So that's another kind of interesting angle to it. But we can't really address this question without better ways of comparing satellite measurements of volcanic processes in different settings with different uncertainties in different contexts. So we kind of moved on quite a bit from then. So this is work that was part of my postdoc in Bristol. One of the things that I contributed to was putting together a global catalogue of volcanic deformation measurements in different parts of the world. And that was in collaboration with colleagues at Cornell University in the States and at the Smithsonian Institution, and also a large group of postdocs and PhD students in Bristol who all spent some time doing this. And we managed to compile new information that hasn't been kind of pulled together from different sources before, including kind of primary information, so like displacement area of signals that are measured, the rates of the signals that are measured, and then some secondary information, so things that are like depth to magma reservoir and distance from the volcano, which to some extent require some interpretation. Normally some assumptions about the properties of the crust, for example, that it's elastic, that there's a viscoelastic shell, magma reservoir. So there's some variation in the data set there, depending on the methods that people have used. But nevertheless, we can see some kind of broad trends from looking at this global data set. So the most obvious one is that a higher proportion of INSAR measurements capture non-magmatic processes. And that's largely because with INSAR we look everywhere, but with ground-based instruments we tend to look where we think there's something interesting to look at. So they're centered on volcanic edifices where there's an expectation of magmatic deformation taking place. We can also say something about the distribution of depths and locations of deformation sources. And I'm saying sources here as opposed to magma reservoirs because what these sources are is something that you could discuss or argue about also. But this plot shows estimated depth from some sort of source inversion. There's a variety of different modeling types in here. On the y-axis, and on the x-axis is different distance from volcanic vent. So where these deformation events could be linked to a specific eruption, it's distance to eruptive vent. Where it can't be, it's the distance to the most recently active eruptive vent. And the interesting trend there is the majority of data fall underneath volcanoes, as you'd expect. But you have about a quarter of the observations that are more than 5 kilometers away from the nearest active volcano. And that's, first of all, kind of a useful bit of information for volcano monitoring, because it demonstrates that quite often if you place a monitoring network close in around the volcano, you'll miss signals that are pertinent to that volcano's activity. So a good example of that is the recent unrest at Nevado de Ruiz in Colombia. So we tried to look at the deformation taking place there with Cosmo SkyMed imagery, which has a very small footprint. It's about 45 kilometers across. And we completely missed a massive uplift signal, which is about 15 kilometers to the south of Nevado de Ruiz, which was picked up on a broader swath image, almost incidentally when people were looking for something else. So I think that's a kind of useful observation to make. But more than that, it tells us something about the complexity of volcanic systems. That you have some magmatic systems that appear to be not directly associated with the volcano, the nearest volcano that we know to be active. In some ways, that's a matter of volcanoes not appearing, for example, in the Smithsonian catalogue because they don't have historical activity. In others, for example, at the Bay of Plenty in New Zealand, which is part of the Taupo volcanic zone, it's more likely that this is just part of a very large caldera rift system, which is not particularly associated with any feature on the surface. So this is obviously quite a big simplification of a lot of data. This is just an example of the complexity of information that goes in there. So there's a lot of detail in this figure. I'm only going to go through a couple of bits of it. But this is data from an episode of unrest at Chile's Cerro Negro volcanoes on the Ecuador-Colombian border. So most people haven't heard of them because they don't have any record of historical activity, but in 2014 they entered a phase of unrest with multiple episodes of seismicity escalating to a point where there are several thousand tiny seismic events every day. So this was of great concern to the monitoring agencies in Ecuador and Colombia. They responded to this by installing some monitoring networks around the volcanoes. And one of the interesting things that came out of this was the discovery that there was uplift about 12 kilometers to the south of volcanoes in what turned out to be an ancient caldera rim. And what we could see with the INSAR was that this uplift was a long way offset from most of the seismicity, which is where this fault plane is here. And this is actually a fault plane for the largest event in the sequence, which is magnitude 6.8, which we managed to find a good fault plane geometry from the INSAR for and place over in this area. So we think that these kind of offset deeper sources are a fairly common feature of magmatic systems. And it's kind of summarized by every individual point in this figure here. So if we think about INSAR observations at volcanoes as a whole, this is a summary plot. There's histograms of the number of events at a particular depth and number of events at a particular offset. So it's a simpler summary of the previous couple of slides. The trend in this axis is mostly associated with uncertainties. As things get deeper, the magnitude of deformation produced at the surface by volume changes at depths gets smaller, so it falls below our measurement threshold. So this trend here is largely associated with measurement limitations. But this one isn't. There's no reason that it should be easier to detect deformation at a volcano than further away, because with INSAR data we're looking at 100-kilometer swaths, and if you process the data you tend to do it in the same fashion. So I think this is a believable and quite an interesting trend. And I think one of the more exciting aspects of this trend is where you have lots of sources which are within kind of 5 to 10 kilometers of an active volcano. And I think that tells us something about the way that magma is stored in mush zones, particularly around active volcanoes. And if we try and understand something about the complexity of that deformation, that can tell us something about the way that magma is capable of moving between deformation sources in that sort of area. So in summary, you have multiple deformation sources at the same volcano. We now have a long enough period of observation. We can actually see multiple cycles of deformation at the same volcano. And the source location is not necessarily the same thing as the reservoir location. A volume change at a volcano could be associated with the influx of juvenile magma. It could be related to phase changes, to crystallization, to gas exsolution. These are things that have been demonstrated at a couple of volcanoes like Okmok and Aleutians, for example. And I think this relationship between distinct deformation sources is really interesting, because you can look at it to try and understand processes, for example, porous flow through a mush zone, where you have coupled deformation, uplift in one place and subsidence in another. You can look into mechanisms for melt or volatile movement associated with those types of coupled signals. And also, as in the Chilo's Cerro Negro example, it tells you something about local stress changes around the volcano. So an important step to be able to get at that sort of questions is being able to separate out volcanic signals that are associated, so they are caused by the same process, underlying process, or volcanic signals that are independent from each other. And the method that I'm going to be talking about is called independent component analysis, and it's a useful tool for being able to separate out volcanic deformation from other volcanic deformation sources, from other sources of deformation, for example, tectonic or anthropogenic processes, and also from the sources of noise that we have in INSAR data, which is predominantly atmospheric effects. So there's a few ways you could go about trying to do this. You could have an a priori knowledge of what your signal looks like, but that relies on only wanting to observe things that you've already observed. You can try and increase the signal to noise ratio if you know, for example, that your displacement has a constant rate, or you can use different types of filtering, but that relies on the signal and the noise having different magnitudes. So the approach that I favour is a blind source separation, which allows you to separate out, to decompose a set of mixed signals just on the basis of the signal characteristics which you assume. So interferograms over an actively deforming region are made up of the part that we're interested in, the deformation signal, and several noise sources. So you have spatially correlated noise, which is line A here, atmospheric noise, which is correlated with topography. So when radar passes through water vapor, the radar is retarded by it, so you have a change in phase associated with that variability in water vapor between two different images. and that tends to be correlated with topography. You have linear or quadratic ramps, which are associated with changes in satellite position between two acquisitions taking place. So all of these random variables can be added together in a linear fashion to give you the interferograms. And this is a set of synthetic data. And the point from this slide is essentially to demonstrate that none of these are exactly matched by a Gaussian signal, which is important for the blind source separation method I'm talking about. But when you add them together, they become closer to Gaussian. So that's the central limit theorem. If you add together random variables, you get closer and closer to a Gaussian distribution. So the method that I've been using and trying to get working for looking at INSAR data has two steps. First of all, separation of signals by independent component analysis, and then a test of the signal significance. So whether the independent components you've retrieved actually capture some property of the real world or not. And the method I'm using for that is intergroup cluster analysis. So independent component analysis has been really widely used in medical physics, and it's been used in a couple of other branches of remote sensing. So this is, I think, Severi data, over looking at kind of hotspot information over a volcano in East Africa. And this is a really classic example. This is functional magnetic resonance imaging, so brain scans. And the way that that works is that a set of slices of information about the brain, so related to the blood oxygen level, are used to map patterns of connectivity between different parts of the brain over different times during different tasks. And geometrically, that's actually a really similar problem to satellite remote sensing, although the timescales are completely different. So they'd have microseconds between images being taken, whereas we have something like 35 days. But the nice thing about that, it means there's been a lot of algorithms developed in order to solve this type of problem. So the basis of separating things out on using signal independence relies on some mathematical definition of independence. So the normal way to do that is using kurtosis. So that's the peakedness or the tailoredness of a curve. Another way is something called non-neg entropy, which is a measurement of the difference between a Gaussian distribution that has the same central value and variance as your data set. And either of those can be used to constrain the isolation of independent components. So the algorithm that I've mostly used is fast ICA, developed at the University of Aalto in Helsinki. It goes through steps of centering and whitening data, reducing dimensions using principal component analysis, and then an iterative correction of the estimation of the number of dimensions that you select. So as a demonstration of how independent component analysis looks, a lot of you, I think, will be familiar with principal component analysis, which is another more really widely used method for blind signal separation. So these are just kind of toy examples. They don't particularly represent anything. But I've got 3 input signals, which are very distinctive, definitely non-Gaussian, and I've arranged them into 3 mixtures in a fairly arbitrary way by adding them together in different ratios. And these are a little bit more Gaussian than the individual signals are. Now, if I separate those out using a decomposition to get principal components, the constraint that I'm imposing on the components is that they account for the maximum possible variance of these mixed signals. So you can see the first principal component that I've extracted there accounts for 71% of the total variance of my signal mixtures. So it does a pretty good job. The next one accounts for, 27%. And by the third, I'm only down to 2%. So you can actually account for almost all of this variability with just 3 principal components. So it does a really good job of matching the variance, but it doesn't come anywhere close to extracting what the original signals look like. So the nice thing about the independent component analysis is you can reconstruct what independent components can be mixed together to produce your mixed signals. And this does a reasonably good job. I think you'd probably agree that these first 2 particularly are a good representation of what I put in. This one is a little bit different because it's flipped in sign and the magnitude is scaled quite differently. And that's because when you do a decomposition of that type, you break down your set of mixed signals into a set of components and then a mixing matrix. The 2 of those would multiply together to bring you back to your original data set. And you can have a multiplicative factor which would appear in either matrix. So there's some ambiguity about the sign and about the magnitude of the signal. So the geometry of the problem for INSAR looks something like this. So this is applying the independence component in space rather than in time. I have a set of interferograms which show patterns in space at various time sets, and I break those down into a set of independent spatial components which hopefully tell me something about where the deformation is and its relationship to the other components, and then a mixing matrix where every line of the mixing matrix gives you the contribution of a particular source to the eventual set of interferograms that you have. So in INSAR, essentially this will give you your spatial patterns, and this will give you time series of those spatial patterns to some extent, with that ambiguity in magnitude and sign. So this is an example using synthetic deformation from INSAR, a little bit like what I showed you before. My deformation source is along the top. See, I've got two independent sources that should be retrieved in different components. And then once I add in all the noise, I've got a set of synthetic interferograms that look like that. If I decompose them into independent components and mixing matrices, these pictures labelled A to M show you what the independent spatial components look like. I've got two that very clearly capture the volcanic deformation, the synthetic deformation that I put in, and the rest which are associated with the synthetic atmosphere. And if you associate those with the rows of the mixing matrix, you can see it retrieves a sinusoidal pattern reasonably well, and a kind of little blip introduced there too. So one thing about independent component analysis is you need to estimate the number of independent components you think that you want to get from your data set. And that's something you quite often have to do iteratively if you don't know the dimensionality of your data very well. So there's a kind of a calibration phase until you've got used to the data set and know how many independent components you want to retrieve from it. And apart from that, you also have the order in which these are retrieved is fairly random, because the way most of the algorithms work to do this, they start with a random seed point. So you need to have an alternative way of working out, without going through and looking at them, which of these independent components are likely to be the ones that you're interested in. So the way that I do that is using a cluster analysis of the spatial components. So these are two independent groups of data. Because in INSAR, atmospheric features depend very much on the direction from which the satellite looks, we would expect the atmospheric components to be essentially random and different from different sets of data, whereas the deformation should be the same if you're looking over the same time period, or at least similar enough if you have a similar angle. So an approach for doing this is breaking down your data set using a kind of jackknife approach, so dividing it into two separate sets arbitrarily. Or if you think your deformation is constant over time, you can divide it through time. And that allows you to reasonably automatically pull out the signals that you think are interesting. And from that, you can go back and use your components with the corresponding rows of the mixing matrix, multiply them out to have a reconstruction of the interferograms with only the deformation and without the noise. And that works relatively well. So the important things that you can get out from this are cleaned up signals which are useful for modelling, and also a test that these things that I put in are actually independent of each other and not connected, which I think for volcanological problems is a more useful result. So a couple of places where I've applied this. In Calbuco in Chile. This was quite a famous eruption in April of 2015. One of the most notable things about it was that it was very, very fast. There were only a few hours of warning associated with elevated seismicity. We looked at interferograms in the months preceding that, and also several years before that. We didn't find any evidence for pre-eruptive inflation, as you do at some other volcanoes. And since petrological studies of the volcano have kind of verified that most likely this eruption was associated with some sort of magma reservoir reorganization rather than an influx of fresh juvenile material. So this is kind of an end member test for the independent component analysis. We would expect to have a mixing matrix which looks something like this. An independent component which is associated really with just one date, which is the date over which the eruption took place. And we know the spatial pattern of the deformation because it was co-eruptive and relatively easy to find. So if I break that down using the independent component analysis, these normalize mixing matrix rows, and you can see that's very much what we get. We have one source, which is the eruption, which dominates the rest of the data set, and that's the red triangle that corresponds to this one here. And then we have, interestingly, a few things which repeat and appear in different images. And that's, if you're interested in technical INSAR processing, that's interesting because it means that we have repeated atmospheric patterns which we could recognize if we had larger data sets and removed from our analysis. So this is what the reconstructed data from Calbuco looks like. This is the input interferograms. This is the reconstruction. And this is the noise that we've managed to remove. You can actually do an even better job of isolating that signal if you apply the independence constraint to the time series instead of the spatial patterns. But that's generally quite a challenging thing to do because it means that the size of the covariance matrix you have to calculate in order to do the decomposition ends up being unmanageably large. So if you're doing that sort of method, it tends to be kind of a very limited spatial area that you'd want to apply it over. So the opposite end member to this is the paracretine lava flows in Mexico. So they were formed during this monogenetic eruption in the 40s and 50s. They're hundreds of meters thick, and they're a good test case because the INSAR measurement of the lava flow subsidence there is really well constrained. Lots of people have looked at it, and it's quite distinctive pattern. So you've got 3 patches of subsidence associated with the thermal contraction of the same lava flows. So they're caused by the same mechanism, which means that we'd expect them to come out as one independent spatial component. And we'd expect our mixing matrix rows to be relatively flat. So this looks like a little bit of an abstract figure, looking at it again. But the top row here shows all of the interferograms that were input data for the independent component analysis. You can see there's no real obvious features in there, except perhaps in the very long time span one. But if we take the independent components from the 2 separate data sets, it does a reasonably good job of reconstructing the same patches of lava subsidence, which is exactly what we'd expect to see. All of them pulled out in the same component because they're caused by the same process. So it's reasonably successful in these areas, which means that when we start to go and look at more complicated places where we have multiple sources acting, we know that it's compatible with the type of signals that we generally see with INSAR. And if we another test for this is we reconstruct the subsidence rate from the independent component in the mixing matrix, it compares very favorably to previous measurements with different data sets of lava subsidence in this area. So there's more detail of this method if anyone's interested in trying to apply it to some other applications in the article. I'm going to leave deformation there and move on to degassing. So this is kind of a simpler methodology, but I think it's quite an interesting science question. And it's similar in that it's about trying to extract quite subtle signals out of large data sets using the fact that we have a really large data set. So instead of doing a decomposition or something that uses the full temporal richness of the data set, this is actually where I've taken more than a decade of MODIS and ATSR retrievals of aerosol and cloud properties, and essentially just taken averages over a really long time series to try and find out about processes that are relatively subtle. So the thing that I was wanting to address was whether or not passive degassing from volcanoes, so the emission of sulfur dioxide, has an impact on local cloud properties in the long term around volcanoes. And the test for doing that was comparing average aerosol optical depth and cloud properties upwind and downwind of these passive degassing volcanoes. So why is this something that we're interested in? At normal atmospheric pressures and temperatures, water vapor requires a particle, a solid or a liquid surface for condensation and formation of cloud droplets. And that can be aerosol from lots of different sources. It could be from dust, it could be from sea spray, from gas reactions in the atmosphere. But we're talking about particles, a fraction of a micrometer across, that eventually lead to droplets of 10 to 20 micrometers across, which lead to rain droplets which fall when they reach a couple of orders of magnitude larger than that. So the effect that I was trying to test the importance of is indirect aerosol effect. So the direct effect is when you have the scattering and absorption of solar radiation from aerosol within a cloud or within the atmosphere. The first indirect effect is associated with the action of those aerosol as cloud condensation nuclei. So if you have more cloud condensation nuclei, you potentially have more droplets. that means the same amount of water is spread over more nuclei, so you have more droplets but smaller droplets. And the consequence of that is that the cloud looks brighter and it reflects more solar radiation back into space. So this first indirect effect is droplets becoming smaller. The second is that drizzle is suppressed, so droplets never reach that critical size that they need in order to fall as rain, but they stay suspended in the atmosphere for longer. So you have brighter clouds that last for longer. And this matters because the impact of aerosol is something that we don't really know all that much about. The plot on the right is from the IPCC assessment report. Across the x-axis, the components of radiative forcing. And if you look at this box here, it's aerosols and precursors. And you can see that there's quite a large, both a large impact, but more importantly in that, really large uncertainties in that box. So if you notice, this is the uncertainty in aerosol and cloud forcing. And you can see that that error bar actually goes right off this plot. So if that was to scale, it would come all the way across to this side of the slide. So it's one of the things that we understand the least about. Within that, if you consider just natural sources of aerosol, volcanic SO2 is one of the largest sources of natural emissions and also has the largest error bars. So it's a kind of important component for understanding the atmosphere as a whole. And one of the reasons it's important is not so much that the magnitudes are large, but we use a pre-industrial baseline during which there weren't measurements in order to compare our current atmospheric processes too. And the volcanic SO2 is a major part of that pre-industrial baseline, which we don't really understand as well as we could do. So we know that volcanic emissions from passive events have an impact on clouds from specific case studies. So these are volcanic tracks from the South Sandwich Islands in the Southern Ocean. So you probably can't see very well, but there's a whole string of volcanoes coming down there. This is Montague and this is Saunders. They both had high degassing fluxes on the day that these images were acquired. And you can see there's these really bright features distinctive from the cloud deck stretching out from the volcanoes. And that's associated with the cloud seeding that comes from the SO2 and its conversion into aerosol in the atmosphere. And you can see within that track, you have very tiny droplets, so right down at the bottom of this scale, relative to everything else in the image. So though they look about as bright as these clouds, they actually have distinctive properties, much smaller droplets than on the right. Another example from the opening of the Hallamama event at Kilauea, you can see a large aerosol plume coming out to the west of the volcano. And in the middle of that, you have the lowest suppressed cloud droplet radius. So those are the signatures for an aerosol indirect effect that we're looking for in the global datasets. So the way I tried to approach this, because these signals are relatively subtle, kind of low magnitude, was to use as much data as we possibly could. So that's cloud and aerosol retrieval information from the NASA satellites, MODIS, both from Aqua and Terra, which have a daily acquisition everywhere in the world, and supplementing that with AATSR retrievals and the Globe aerosol dataset. So I would select data around active volcanoes that we think had a significant passive degassing flux, and then reproject them into polar coordinates and rotate them. So it's a very simple method. Essentially, rotate around the location of the volcano so that the downwind direction, according to the ECMWF reanalysis data, could be stacked on top of each other, and the upwind stacked on top of each other. And the importance of doing that does allow me to compare directly the part of the atmosphere that we thought was being affected by the volcanic emissions to something that's more or less in the same place but was unaffected. And from that, you get a set of polar plots that look something like this. This arrow shows the wind direction. This is the sector that's downwind, and this is upwind. And by comparing the properties of the upwind and downwind, we can say something about what impact is associated with the volcano as opposed to anything else that's going on meteorologically in that area. So a particular challenge for this was a selection of case studies. So to be honest, I started off looking at Etna because that seemed like a good place to start for a large SO2 flux. But the effect at Etna was really, really hard to pin down. And I think part of the reason for that is that volcanic aerosol are only really important where you don't have other sources of aerosol. So where you have lots of aerosol from industrial processes, and the impact of the volcanic aerosol itself is pretty negligible. So we couldn't pin it down at Etna, largely because when I tried this sort of approach, it worked much better when I centered my, my rose diagram on Naples than on Etna itself. It was a much bigger source. So I then pinned it down to looking at remote ocean islands, which were isolated to a distance of a few hundred kilometers, and isolated from other sources of anthropogenic aerosol. I also picked volcanoes that were persistently active, but without highly explosive eruptions. So the definition of persistently active is variable a little bit here. So there's a Kilauea, which has a fairly constant high SO2 flux, Piton de la Fournaise, which is persistently active in the sense that it has lots of small eruptions, but is not really a big SO2 source. So to test that there weren't other major sources of aerosol at these volcanoes, to make sure it was a fair test, I then looked at the relationship between aerosol optical depth and wind speed. Because in the absence of all other sources of aerosol, you'd expect most of the aerosol to be associated with sea spray, which is directly proportional to the speed of the wind above the ocean. And that relationship is reasonably convincing for the 3 volcanoes that I looked at in more detail. So we take that as good evidence that there's no anthropogenic aerosol within 50 kilometers. Well, perhaps that's a little bit strong, because we'd expect there to be ship tracks. Just that anthropogenic aerosol is not the dominant source of aerosol in that area. And more than that, there's another thing which I'm sure you might have spotted already. If you're comparing upwind and downwind cloud properties and aerosol optical depths, you might end up looking at an orographic effect. So that is when you have cloud formation associated with the lifting of a warm air mass, which is saturated with water vapor, over some topography, you have cloud formation and water droplet formation associated with that in a way which is systematic with wind direction. So I picked a few examples, control islands, which have similar widths and similar heights to the volcanic examples as a point of comparison to see how this compared. So that was Kilauea was compared to Fiji, for example, La Réunion to Tristan da Cunha, which is probably not a source of SO2. Though that's quite a difficult thing to prove. Okay, so this is what the results look like for aerosol optical depth. So these figures here, the distances are in kilometers. This direction is downwind, this direction is upwind. And you can see over the volcano itself you have a sudden increase in aerosol optical depth, which then tails away as you get away from the volcano. And you see something similar at Usur, and a much smaller effect at Piton de la Fournaise. And that's the size of these aerosol optical depth anomalies are roughly proportional to the SO2 fluxes from those volcanoes. So at Kilauea, which has the largest anomaly there, you can see there's a good correspondence between this peak in aerosol optical depth and the trough in cloud effective radius, so droplet size downwind. So we can associate this elevated feature, where most of the aerosol seems to be, with the smallest cloud. You can also see there's increased amount of cloud just over the volcano, but that the peak in the cloud optical depth doesn't correspond perfectly. It comes slightly before the trough in cloud effective radius. So we have an additional effect here, which is probably that there's some water vapor coming out of the volcano, which will also enhance the effect of cloud formation. You see the same thing throughout all 4 seasons at all volcanoes, although it's more convincing perhaps during some seasons than others. And the background levels of aerosol and background cloud properties are quite variable across the different seasons. So every colour there represents a 3-month period. And we also see a similar sort of effect between the MODIS data and the ATSR, although something that this highlighted, which I think that needs a little bit of further investigation probably, is that the retrieval values for aerosol optical depth and cloud effective radius are quite different between the 2 satellite instruments. I mean, that's essentially because they use slightly different wavelengths in the retrievals. So even though the values are different, you still see the drop down in the volcano. But the story is not identical, although the main features are the same for the different instruments. And if you compare the volcanoes to the control islands, you can see that you don't see these very distinctive features associated with them, although the topography is similar. They're found in the same bands of ocean. So if we are only detecting an orographic effect at the volcanoes, we might expect to see something similar there. So this plot is from La Réunion. It's it was my attempt to try and work out what kind of aerosol we were actually seeing the effect of at this volcano. So on the left, this is from intereruptive periods, according to observatory records. So when there wasn't any eruption ongoing, there weren't any active lava flows. And on the right is during eruptions. So the top row here is aerosol optical depth. So a red colour means there was excess aerosol. The bottom is cloud droplet effective radius. So a blue to purple colour means that droplets were smaller. So the two features that we were interested in. And you can see during the eruptive periods, both of those effects are elevated, which suggests that whatever the source of aerosol is, it's associated with eruption at the volcano. But it doesn't disappear completely in between eruptions either, which is interesting and suggests that there is some aerosol source from the Union, even outside periods of eruption. So you can kind of simplify this a little bit by going straight for looking at top of atmosphere shortwave flux instead of messing about with looking at cloud properties, because I guess that's the kind of, apart from looking at local meteorological conditions, looking at the impact on radiative balance is really what you're interested in here. And these are the differences between upwind and downwind wind shortwave top of atmosphere flux at Kilauea, Yasur, and at Piton de la Fournaise. And you can see at Kilauea, what's particularly interesting about this, you have an anomaly, so much more radiation reflected back into space immediately downwind of the volcano. And then you have a kind of secondary peak at a greater distance, which is a difficult thing to explain when you're looking at really kind of average data like this. But it seems likely that it's associated with the reaction distance from SO2 coming out of the volcano to the point at which aerosol is produced in the atmosphere. At Yasur, we have something a little bit more complicated, which I think is harder to interpret. You might have noticed in some of the earlier plots of Yasur, it looked like there was a kind of long gradient which went across that part of the atmosphere. But on average, you have a brighter cloud downwind of Yasur than upwind. So that's a similar trend. And at Piton de la Fournaise, the effect is much more local and much smaller, which is exactly what we saw from looking at the cloud droplet effective radius. And the nice thing about doing it this way is that you kind of get independent confirmation of what we see from looking at the cloud properties, but from a retrieval which is completely independent of those. And these are the control islands. So this is kind of the opposite case. We don't really see the same effect, just to demonstrate that it's not orographic. So the nice thing about this is we can demonstrate that passive degassing does produce indirect aerosol effects that have a net impact on a decadal timescale, which is something that's otherwise quite a hard thing to measure and get at. You know, we assume it does happen, it kind of gets put into models, but actually detecting it is quite a challenge because the magnitude is so low. It's roughly proportional to SO2 flux in the examples that we've been able to look at. And I think probably the most important impact that you can draw from this is that it's some useful information about the conditions of the pre-industrial atmosphere. These processes were important to the order of magnitudes we've been able to measure in a pristine ocean all over the world before there was a lot of anthropogenic aerosol. And that's all I have, so thank you.